All right, hello everyone. I have to start by saying I noticed the questions came from a certain demographic. We started off with a Wonder Woman commercial, everyone. So, ladies, let's show better participation next time. All right, so I'm Kimberly Sokal. I am the Igrins postdoc here at the University of Texas. So Igrins is an astronomical instrument that we use for science. And I'm going to tell you guys all about it. And thanks to Major Merger over there for giving us a good introduction about different kinds of light, because it's going to matter. So Igrins is the Immersion Grading Infrared Spectrometer. The two most important things about it is that it's high spectral resolution and a near-infrared instrument. So I'm going to go really deep into detail on those two things, high spectral resolution and near-infrared. And after that, hopefully this name will mean a lot more to you. So the basic principle of astronomy is that we can use the light from the sky around us to learn about the universe. But when we look up, like in this image as well, we see that most of the light looks like white dots or white scattered light. And we can learn so much more if we're able to split that light apart, such as with TV, we tend to prefer color versus black and white. Now, the most familiar to you in a case where nature splits up the light for us is with a rainbow. So what's happening is that the water vapor in the air is acting as a prism and splitting up the light. Pink Floyd taught us all the spectrum as well, just in case that's more familiar to you. So we have the white light coming in, and a prism is splitting it up into the most basic colors are the ones that are the easiest to see. So here's the spectrum of the sun. This is what a spectrum can look like. So we have the amount of light, which we can call that the flux, versus the wavelength, and that can correspond to certain colors. So we see at the bottom. Now the reason we want to look at spectra is because of all this structure that you can see. We can see a lot from images, but this tells us more. So you can see we have this shape, and we also have all of these features. Now we call these spectral lines. So different elements and molecules all have their own spectrum, and those are just made up of those spectrum lines. You can see here is what hydrogen looks like, for instance. So you can think of these as a fingerprint. So when we look at a spectrum of an object, we can look for these fingerprints in that spectrum. So as XKCD shows us, if we look at the sun, we can find iron, we can find sodium, and here's where you find the lines from the giant sunglasses. So what we want to do to learn the most about an object is to see as many features as we can. We want to see as many spectral lines. So if we can split up the light into smaller and smaller pieces, we call that having a higher spectral resolution or a resolving power. So we're aiming for a higher spectral resolution. Now Major Merger already showed us this electromagnetic spectrum and told us that I'm working in the infrared. So just a reminder that this is just red words, longer wavelengths than that familiar rainbow that we were looking at before. Now this is redder than what you can see by your eye, but there are a few things that you guys may already be familiar with, like night vision goggles or heat sensors in movies. So here's some infrared images. In here, what you're seeing is that the brighter, the white and the yellow, show things that are hotter, like eyes, mouth, or a forehead on a child. But things that are cooler, such as hair and fur, are shown as dark purple, and those are doing their job. They're insulating, keeping the heat in. Now, something that may cause you more pause is that we can see things that we can't see with our eyes. For instance, this hair dryer, you can actually see the hot air coming out. So for that reason, the infrared can actually be more useful than the optical, depending on what you're looking at. Sometimes you can actually see through objects as well, such as dust, or as this gentleman is showing us, you can see through a black plastic bag, and you can see all of his fingers. So that's one of my favorite things to do at astronomy camps, if I have an infrared camera, is to play how many fingers am I holding up, because that's just very bizarre. So we can do this in space. I'm really glad I chose Andromeda instead of the ones that we already saw. So we have the optical image right here, and it's mostly stars and scattered white light. When we look at the infrared, now the light's no longer scattered, so you can actually see the beautiful spiral patterns coming out. So as you heard, Igrins is in the near infrared. So that's the part of the spectrum that is closest to the optical. It is just redward of what you can see by eye. We call it 1.5 to 2.5 microns. So that brings me back to Igrins, the immersion grading infrared spectrometer. So basically, it's a sort of camera, that's it right there, that attaches to the back of a telescope. We're using it to gain a lot of light collecting power. And it gives us high spectral resolution, near infrared spectra. Now, it's really important to us here in Austin because it was developed at UT Austin. And that is what these last two words are that you may not be familiar with, immersion grading. So those are what's acting as the spectrum, as the prism. But they are actually more precise. And they do such a good job. Igrins is way more compact than most spectrographs. And it has a huge wavelength coverage. So because of these immersion gratings, we actually do 5 to 30 times better than our competitors, which is a huge factor. So Igrins was commissioned, and its home base is at McDonald Observatory in West Texas. It's there right now. It's on the 2.7 meter Harlan J. Smith telescope. And it has also spent some time recently at the Discovery Channel telescope in Lowell Observatory in Arizona. We went there just to get a little bit more light collecting power, because it's a 4-meter telescope. Now, a traveling instrument means that someone has to travel with it, so that's me. I have flown in lots of planes and cars. It also means I'm an occasional truck driver, driving this really important piece of equipment around. So every time we put an instrument on a telescope, it's a really big deal. So here I am showing off each time we got Igrins on a telescope. So here is the Harlan J. Smith and the DCT. Now, of course, to have such an incredible instrument requires an incredible team. So I wanted to show you guys my current Igrins lab and science team. We are also partners with KASI, which is the Korea Astronomy Space Science Institute. And I wanted to point out right here, Dan Jaffe, who is our PI, the principal investigator for Igrins. All right, so now that I have given you guys a good introduction to Igrins, you probably want to know a little bit what we can use it for. Yes? All right. So I'm sorry for all the words that I put on the screen without pretty pictures. But the thing is that with Igrins, we can do so much science with it. So thanks to having high-resolution near-infrared spectrograph, it gives us a very unique set of capabilities and skills. So I listed a few of these over here in our toolbox. And we use those to investigate many different fields in astronomy. Now, some of those match up. I'll touch on that a bit. So I'm going to talk about a few of these in no real order. So one of the most important things when it comes to the science that we can do really well with Igrins is that stars, if they are cooler, they're going to peak at longer wavelengths. So you may remember that solar spectrum I showed before. Maybe not, but it's about this one. And it peaks in the optical. We put that familiar rainbow right there. And by peaking, what I mean is that the most light is coming out of those wavelengths. That's probably one of the reasons we see optical with our eyes. But if we have a cooler star, which is almost anything that's lower mass as well, then it's going to peak at redder and redder wavelengths. So if we had a low mass star as our sun, we might see at infrared wavelengths instead. But so that's one of our secrets. We are using the infrared to look at cool objects, and we study those in their own right, as well as to study things around them, if they're in binary systems or they have exoplanets. There's one really unique thing we can do in the infrared, and that's measure magnetic fields. So it doesn't look like this, but who remembers doing this in science lab? We have a few people. So basically what happens with this is you have a magnet, and you cover it in a piece of paper, and then you pour magnetic filings on it. So it's tracing out this magnetic field that you can see. Otherwise, you can't see that by eye. So our Earth has one, as well as the sun and many stars, but they don't look like this. We draw this to talk about it. That's it. So when we take pictures and images of stars, we can't just see the magnetic field, and we can't just throw magnetic filings at them to see it. That'd be nice. But so we're lucky in that the magnetic field can alter the spectra. So what happens is that a strong magnetic field can change the levels between different energy states. That sounds really complicated. But all that's happening is that we take a single spectral line, and a strong magnetic field can split it into two. Now, that sounds complicated, but let me just show you. So this is from my real paper, and I think you guys are up to speed with it on me, so you should be happy about that. So here's an Igrins spectra, that black squiggly line. And on the top, I'm showing what happens if there would be no magnetic field. You see there's just one line, and it's very deep and very obvious. If we add a strong magnetic field, it splits into two. Now we have two little troughs on each of those. So that means that this star has a strong magnetic field. Now this is called the Zeeman effect, and it's easier to measure at longer wavelengths. So if you're trying to do that in the optical, it's going to be very difficult. But in the infrared, that's where it's at. So why do we want to measure this, other than the fact that it is hard? We don't know too much about it anyway. Well, magnetic fields are very strong, and even astronomers, we try to use them as a scapegoat. Like, oh, that didn't work out quite right. It was probably just a magnetic field. So I actually have a quick demo for you guys, just to show you why magnetic fields matter. So, thank goodness for pockets. Yeah. So, I have a spoon and a refrigerator magnet. This is a tiny little ladybug. The magnet is about the size of my fingernail. So let's test magnet versus the gravity of the entire Earth. Now what do you guys think is going to happen? You can probably guess since I'm showing you. Alright, there we go. Tiny ladybug magnet holding up my spoon versus the mass of the entire Earth. So, even though the gravity and light are really important when we talk about things like star formation and how planets are forming, magnetic fields are really going to come into play, at least in some cases, if a little magnet can hold up my spoon. Also, they're responsible for things like solar flares and sunspots, and those matter in young stars too. Alright, last but not least, I wanted to talk about how Igrins helps investigate star formation. This is primarily what we use Igrins for. So let's walk through this diagram a little bit. So, you have a giant cloud of gas and dust. It's going to start collapsing, and some of the densest material inside will start to ignite. We have a protostar that's going to be completely enshrouded by dust and gas. Optical wavelengths are definitely not going through that. It's going to keep collapsing until we have a star that is surrounded by a protoplanetary disk. Right, protoplanetary. So the planets are going to start forming around it, and eventually it's going to clear away the rest of that dust and gas, and we'll be left with just a star and planets. We have a nice little solar system. So I'm hoping that you guys can already guess why Igrins is the perfect instrument to study star formation. So we have all this dust and gas that we want to look at in the infrared so we can actually see what's going on. Especially these disks are normally not aligned, so we can see the stars, so we have to see through at least part of it. A lot of the stars that are forming planets are the temperature of the sun or colder, so we still want to go to the infrared. And with high spectral resolution, we can see more detail, so we can actually learn more about those stars. As Major Merger pointed out, it's always helpful to do multi-wavelength things. So I wanted to include these, because this is some of the most cutting-edge science that pops up in the news these days. So this is a protoplanetary disk taken in the radio wavelengths. And they can actually start to see gaps in structure in these disks. And that might be, some of these might be due to planets, which is so exciting. But I want to say that studying the star in the middle, which we need the infrared for, is super important. I'm going to be bold and say it's like you're making cookies. You can have a really good recipe, and you can make a perfect batter. But if you don't know how the oven works, you're not going to end up with cookies. So this is where Igrins and my research come in. We're trying to study those host stars, and then we can develop a full picture of the star formation. So I'm getting really high-quality spectra using Igrins to study young stellar objects, and I can even measure their magnetic fields, as I showed, to work on this picture of star formation. I wanted to quickly show you guys my spectra. All you have to remember from this is how detailed it is. And now I'm showing 2 pages right now. We actually have 12. So it's an incredible amount of information. And then I wanted to leave you with some pictures from behind the scenes. An incredible amount of work goes on just to get those spectra. And that's even before we start observing. So it goes from working in the lab, making sure Igrins is put together and doing maintenance, to getting it to the telescope, to attaching it to the telescope, to even driving to go do our observations. It's a lot that goes on. So if you ever want to hear more about it, feel free to talk to me afterwards. All right, thank you.
Thank you, Starry Nights. And so we have some time for some questions. Yes, we got a lady over here.
Nice work. Thank you. Those are some great questions. So her question was, she's assuming it's quite expensive, so why didn't we make two instead of just driving it around? So my answer for that is, one, it is quite expensive. And so we operate it as, we call it a PI instrument, meaning we own it in a huge part with McDonald Observatory, but we also then do travel with it. So our next stop is Gemini Observatory in the south, because there's a lot of objects we can't see up here in the northern hemisphere. So money can come into play. It would be great to have another Igrins. So everyone has an optical spectrograph. So even though we like to boast that we're 30 times better than other spectrographs, I wouldn't mind if everyone had one. That would be great. The other thing is the CCDs that we use to actually take the images are, no one currently makes them to high enough quality. So making another one, there's going to be a little bit more work to do there. And the second part of the question was, what do we use for the prism? So that's where the immersion grading comes in. That's our sort of prism. It's made out of silicon, and we have a lab on campus. It's on the 17th floor of our building, and they make them by hand, and they are currently working on developing a bigger, fatter version of Igrins for the 30-meter GMT telescope, and they're making gradings for that right now.
Yeah. Right in front.
That's a great question. So her question was, how far away are these star-forming regions, and how old are they? So we are, the spectra that I showed of the magnetic field and the disks in the radio, those are actually, that's the closest known disk to us, which is why it is in such high detail. Other things about 3 times farther than that. So those are still all of the closest regions of star formation that we have in the galaxy. As for how old, the oldest is about 10 million years. So that's quite young when you talk to most astronomers. For me, that seems pretty old. I think like 3 is young.
In the back right there.
All right, I was asked if there are commercial spectrographs available to work on personal telescopes, such as a 10-inch or something. There certainly are. I know that even just for classrooms, they've developed some that you can put in, such as an app on your smartphone, and even use that. I can't think of any of the names off the top of my head, but they certainly exist.
Right there.
Our spec.
Do you have a question too? Up in the balcony?
Okay, good question. So he asked how Igrins compares to the spectrographs that are installed on the Hobby-Eberly telescope, which is one of the big telescopes at McDonald Observatory. So they are more in the optical part of the spectrum. In the fall, they're actually bringing one that is also in the infrared, and it is working at wavelengths right in between the optical and Igrins. So all of them can have a great synergy and work together. So we're actually looking forward to that.
Also in the balcony?
All right, so he asked a burning question on whether Igrins is high enough quality to find elements in protoplanetary disks. So when you're looking for elements in protoplanetary disks, most of what you want to look at is with ALMA at the radio wavelength. So they're looking for things like methane and such. But what you can hopefully find, if you have enough light collecting area and you do it just right, is maybe look for some elements in exoplanets. So one of our graduate students is working on this right now. So what she's doing, and the only way that this works, is that she's working with a molecule, water, whose fingerprint, as I talked about with lots of lines, there's thousands of lines all across the Igrins spectra. So because there's thousands, she can add them up. So so she's hoping that she can use that to detect it. But she's still working on that, but we're very proud of her efforts on that.
Okay, last question.
All right, conception to first light. I actually can't answer that because that was far before me. First light was, let me think, 2014, and that would have been, I think, in March or April. So we have a solid 3 years of data so far.
I'm sorry. I want you to ask a question.
Okay, so she's asking how we are able to make images of infrared data because we can't see that with our eyes. So our CCDs are taking pictures, so they're just getting the amount of light that comes in. So if you were just to pull it up, like on your computer, you can make it look you have no idea where it's coming from in the spectrum. You have an amount of light in a spot. So it's the same software that you can use for optical in the end when you're making an image. And then we just alter the colors to try to convey a little bit more of those physics to know what's happening.
Great. So with that, let's thank Starry Nights again.